Next chapter, matrices. A matrix is a rectangular arrangement of numbers, letters, and symbols called elements, usually enclosed in brackets. These are examples of matrices. Elements in a matrix are arranged in rows and columns. The number of rows and columns give the order of the matrix. The order is given as row times column, read as row by column. So A has 2 rows and 2 columns. It's a 2 by 2 matrix. B is a 1 by 3 matrix. C is a 4 by 1 matrix. And D is a 3 by 2 matrix. Matrices can also be represented using bold capital letters. For example, P is equal to 2465. Q is equal to 3187. Other terms used to describe matrices include: a row matrix is a matrix with only one row. If M is equal to 132, then M is a row matrix of order 1 by 3. A column matrix has only one column. If N is equal to 569, then N is a 3 by 1 column matrix. A square matrix has equal number of rows and columns. If A is equal to 10 2 7 15, then A is a 2 by 2 square matrix. If B is 532 681 470, B is a 3 by 3 square matrix. Operations on matrices: addition and subtraction. Matrices can only be added or subtracted if they are of the same order. So a 3 by 3 matrix cannot be added or subtracted with a 2 by 2 matrix. A row matrix cannot be added or subtracted with a column matrix. In matrices, we simply add or subtract corresponding elements. For example, if P is equal to 5912 and Q is equal to 41053, then P plus Q is equal to 5912 plus 41053. That gives us 5 plus 4 is equal to 9. 9 plus 10 is 19. 1 plus 5 is 6. And 2 plus 3 is 5. P minus Q is equal to 4 minus 5 is minus 1. 10 minus 9 is 1. 5 minus 1 is 4. And 3 minus 2 is 1. Multiplication. Multiplication of matrices by scalars. When a matrix is multiplied by a scalar, every element in the matrix is multiplied by the scalar. For example, if A is equal to 6 8 12 16, then 2A is equal to 2 times 6 8 12 16. 2 times 6 is 12. 2 times 8 is 16. 2 times 12 is 24, and 2 times 16 is 32. A half A is equal to a half times 6 is 3, a half times 8 is 4, a half times 12 is 6, and a half times 16 is 8. Multiplication of matrices by matrices. Now, in order to multiply a matrix with another matrix, we first make sure that the number of columns in the first matrix is equal to the number of rows in the second matrix. And then we multiply the elements of each row of the first matrix by the elements of each column in the second matrix, And so in multiplication of matrices, we say it's row times column and not column times row. For example, consider these four matrices A, B, C, and D. A has two columns and B has two rows. That satisfies the first requirement. And so it's possible to multiply A times B. So we have 2, 5 times 3, 4. That gives us 2 times 3 plus 5 times 4. That gives us 26. Can you multiply B times A? No, you can't. B has one column and A has one row. That satisfies the first requirement. But then in multiplication of matrices, we multiply row times column and not column times row. C and D cannot be multiplied by A or B because obviously they have different number of elements. How about C and D? Which one is possible? C times D or D times C? If we try C times D, we've said that the number of columns in the first matrix must be equal to the number of rows in the second matrix. C has one column and D has one row, so that satisfies the first requirement. But then we cannot multiply column times row. We have to do row times column, and so C times D is not possible. We go D times C. D has 3 columns and C has 3 rows. That satisfies the first requirement. And then we multiply row times column. So we have 6 times 1 plus 2 times 7 plus 5 times 3. That gives us 35. Another example, P is equal to 412,356 and Q is equal to 971. So P is a 2 by 3 matrix and Q is a column matrix. P has 3 columns and Q has 3 rows, and so P times Q is possible. We multiply rows of the first matrix by the column of the second matrix. So we have 4 times 9 plus 1 times 7 plus 2 times 8. And then we have 3 times 9 plus 5 times 7 plus 6 times 8. That gives us 59 and 110. Q times P is not possible because Q has 1 column and P has 2 rows. Square matrices are multiplied only if they are of the same order. For example, if A is equal to A, B, C, D and B is equal to E, F, G, H, then A times B is equal to A times E plus B times G, and then A times F plus B times H, and then C times E plus D times G, and lastly C times F plus D times H. For example, if M is equal to 3124 and N is equal to 5768, then Mn is equal to 3 times 5 plus 1 times 6, and then 3 times 7 plus 1 times 8, then 2 times 5 plus 4 times 6, and lastly 2 times 7 plus 4 times 8, giving us 21, 29, 34, 46. Nm is equal to 5 times 3 plus 7 times 2, 5 times 1 plus 7 times 4, 6 times 3 plus 8 times 2, and 6 times 1 plus 8 times 4, giving us 29, 33, 34, 38. And so you see, m times n is not the same as n times m in matrices. M squared is equal to m times m. That will give us 3 times 3 plus 1 times 2, 3 times 1 plus 1 times 4, 2 times 3 plus 4 times 2, and 2 times 1 plus 4 times 4, giving us 11, 7, 14, and 18. Next, special matrices. We start with identity matrix. An identity matrix is a square matrix which is equal to 1, and so when multiplied by another matrix, it doesn't change the latter. It is denoted by capital I. For a 2 by 2 matrix, I is equal to 1, 0, 0, 1, and for a 3 by 3 matrix, I is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Consider P is equal to 3, 4, 5, 1. P times I is equal to 3, 4, 5, 1 times 1, 0, 0, 1, giving us 3 times 1 plus 4 times 0, 3 times 0 plus 4 times 1, 5 times 1 plus 1 times 0, 1 times 0 plus 1 times 1, giving us 3, 4, 5, 1. The matrix P does not change when multiplied by the identity matrix. A null matrix is a matrix where all elements are 0. It's denoted by O, and so O is equal to 0, 0, 0, 0. We take 2 examples. First one, given that P is equal to 0, 2, 1, 3, Q is equal to A, 4, 2, A, and that P times Q is equal to 4B, 9C. Find the values of A, B, and C. In this case, we multiply the elements of P and Q as usual and equate them to the corresponding elements of the product matrix PQ. We shall form equations and solve them. So 0, 2, 1, 3 times A, 4, 2A is equal to 4B, 9C. And so multiplying 0 times A plus 2 times 2 is equal to 4. Then 0 times 4 plus 2 times A is equal to B. Then 1 times A plus 3 times 2 is equal to 9. And finally 1 times 4 plus 3 times A is equal to C. For the first one is direct, there is no unknown, because 0 times A is 0 and 2 times 2 is 4. For the other one, 1 times A is A plus 3 times 2 is 6 is equal to 9. So A plus 6 is 9, and therefore A is equal to 3. The third one, 0 times 4 is 0, and then 2 times A is equal to B. Substituting that in the equation we've just left, 2 times A is equal to B, and therefore B is equal to 6. And lastly, 1 times 4 is 4, plus 3 times A is 3A is equal to C. 4 plus 3A is equal to C, and we already have the value of A. So 4 plus 3 times 3 is equal to C, and C is 13. The example, given that 5, 7, 6, 8 times A, B, C, D is equal to 29, 33, 34, 38. Find A, B, C, and D. In this case, we multiply the matrices as usual and equate them to the corresponding values of the product matrix. So we go 5 times A plus 7 times C is equal to 29. And then 5 times B plus 7 times D is equal to 33. 6 times A plus 8 times C is equal to 34. And finally 6 times B plus 8 times D is equal to 38. Finishing the first two pairs, we want to eliminate A, so we multiply the first one by 6 and the second one by 5. We shall get 30A plus 42C is equal to 174, and 30A plus 40C is equal to 170. We subtract, we get 2C is equal to 4 and C is equal to 2. We substitute the value of C into the second equation. 6A plus 8 times 2 is equal to 34. 6A plus 16 is 34. 6A is 18 and A is 3. The second pair, 5B plus 7D is 33. 6B plus 8D is 38. We eliminate B. We multiply the first one by 6 and the second one by 5. Get 30B plus 42D is equal to 198. 30B plus 40D is equal to 190. We subtract, 2D is 8 and D is 4. We substitute in any of the equations. We do it in the first one. 5B plus 7 times 4 is equal to 33. 5B plus 28 is 33. 5B is 5 and B is 1. Next, determinant of a 2 by 2 matrix. Now, given a 2 by 2 matrix A, B, C, D, A and D make the leading diagonal. B and C make the secondary diagonal. The determinant of this matrix is equal to the product of the leading diagonal minus the product of the secondary diagonal. That is AD minus BC. For instance, the determinant of a matrix 4, 3, 5, 8 will be 4 times 8 minus 3 times 5, giving us 17. Inverse of a 2 by 2 matrix. The inverse of a matrix P is given as P raised to power negative 1. Usually, P times the inverse of P will give us the identity matrix I. To find the inverse of a matrix A, B, C, D, find the determinant, that is AD minus BC. Then, interchange the elements in the leading diagonal, so the matrix becomes DBCA. Then, change the sign of the elements in the secondary diagonal. If it's positive, you make it negative. If it's negative, you make it positive. And so we shall have D minus B minus CA. Then you divide this new matrix by the determinant. And we shall have 1 over AD minus BC times D minus B minus CA. For example, if A is equal to 4 minus 6, 8, 2, the inverse of A will be the determinant is equal to 4 times 2 minus 8 times minus 6, and that gives us 56. We interchange 2, negative 6, 8, 4. Change the sign. 2, negative 6 becomes 6, 8 becomes negative 8, and 4. We divide by the determinant and we shall have 1 over 56 into 26 minus 8, 4. When the determinant of a matrix is 0, it is called a singular matrix. For example, 1, 2, 2, 4, and 3, negative 3, 1, negative 1. Finally, solving simultaneous linear equations using matrices. Now, simultaneous equations can be solved by using the inverse of a matrix created from the coefficients of the equation. For example, 2x minus y is equal to 5, 3x plus 2y is equal to 4. We write the coefficients of x and y as a square matrix. The coefficient of x in the first equation is 2, y is negative 1, and then for the second equation, the coefficient of x is 3, and that of y is 2. Then times xy, and then we equate to the answer 5, 4. To eliminate the square matrix and remain with xy, we multiply both sides by the inverse of the matrix. We have seen that when a matrix is multiplied by its inverse, the answer is an identity matrix, which is basically equal to 1. The determinant will be 2 times 2 minus 3 times minus 1 gives us 7. And so the inverse will be 1 over 7 into 2, 1 minus 3, 2. 1 over 7 into 2, 1, negative 3, 2, times 2, negative 1, 3, 2, and then times xy should be equal to, we also multiply the other side by the inverse, that is 1 over 7 into 2, 1 minus 3, 2, and then times 5, 4. A matrix times its inverse will give us the identity matrix 1, 0, 0, 1 times xy, that is equal to, we multiply the other side and we shall have 2 times 5 is 10, plus 1 times 4 is 14. Then we have minus 3 times 5 is minus 15, plus 2 times 4 is 8, and that gives us minus 7. So xy is equal to 2, negative 1, and therefore x is equal to 2, and y is equal to minus 1. Last example, 2x minus 3y is equal to 3, 3x minus 4y is equal to minus 5. Write the coefficients as a square matrix, that is 2, negative 3, 3, negative 4 times xy is equal to 3, negative 5. The determinant will be equal to 1 because 2 times minus 4 is minus 8, and then minus 3 times minus 3 is minus 9. Minus 8 minus minus 9 is equal to plus 1. And so the inverse will be minus 4, 3 minus 3, 2. Times 2 minus 3, 3 minus 4 times xy should be equal to minus 4, 3 minus 3, 2 times 3 minus 5. The left hand side will remain with identity matrix 1, 0, 0, 1 times xy should be equal to, we multiply the other side and we shall end up with minus 27 minus 19, and therefore x is equal to minus 27 and y is equal to minus 19. Good luck with matrices.
If you want to go on and major in math or do honors in math or do a career in math, you really do need to be good at it. But I think too many people stop out too soon because they've had bad experiences. I think math teachers have a lot of responsibility for that. We haven't taught it so well. We haven't provided the resources that people need. And so I think if you need help, you need to get it, and you need to get it early, and you need to work at it.